The SR latch is the foundational sequential circuit that we use to build all other sequential circuits. The circuit is composed of two cross-coupled NOR gates, where the state that we are storing is called Q, and the complement of the state is stored in Q prime. To demonstrate how the circuit works, let's assume that we do not know the values of the state or its complement, but that we will input 0 and 1 to R and S. If either of the inputs to a NOR gate is 1, the output is 0. So we know that Q prime will be 0 regardless of the feedback from Q. Since R and Q prime are 0, the state will be set to 1. Let's change S to 0. When both S and R are 0, both Q and Q prime will hold their values. Now, let's change R to 1. Because R is 1, the state will reset to 0. Because both the state and S are 0, Q prime will be 1. Finally, let's change S back to a 1. Because both R and S are 1, the state and its complement are now both 0. Since we do not want the state and its complement to be equivalent, we say that this input combination is forbidden. We can describe the SR latch's behavior with two tables. We use the first table when we know the inputs and the value of the current state Q, and we want to know the circuit's next state, Q+. So here we see that the first input combination holds the current state into the next state. The second input combination resets the next state to 0, hence why R is 1 for reset. The third input combination sets the next state to 1, hence S is 1 for set. And the final input combination is forbidden. We use the second table when we know our current state and our desired next state. The right columns tell us what input combinations will allow us to excite the desired next state given the current state. Now, the SR latch is useful, but we can make its operation simpler by forcing the two inputs to be complements of each other. Now, when we make our new data input 0, the input's complement will be 1. This will reset the state of the latch to 0. Q prime will also become 1. When we change the data input to 1, the input's complement and the Q prime become 0. Then the state of the latch is set to 1. We can describe the D latch's behavior with the same tables as before. Notice that the next state is always the same as the data input. Much simpler, huh? When we design sequential circuits, we want to synchronize the times when all state storage components store new data. We synchronize these components with a signal called the clock that oscillates between 0 and 1. To help synchronize the components, we can add a clock command to our latch that acts as a gatekeeper that allows the latch to change its value only when the clock's value is 1. For example, suppose that the data input has the following waveform, and they want to determine the state of the D latch. Initially, we do not know the state of the flip-flop, but whenever the clock is 1, the latch can change the state, and the latch's state will equal the data input. Whenever the clock is 0, the latch will hold its state constant and ignore the data input. This gated latch is not ideal, though, because we must hold the data input at the desired input value for half of the clock cycle, and that cuts down the time that we have to perform calculations during the clock cycle in half. An alternative clocking method for synchronizing state storage components is called edge triggering. When we use an edge triggering clocking scheme, we call the latch a flip-flop. When we have a positive edge triggered flip-flop, We draw the circuit components as shown above, and the flip-flop reads and stores the value of the input only when the clock rises from 0 to 1. So again, we do not know the flip-flop's state to start, but at the first positive clock edge, the data input resets the state to 0. Then, at the second positive clock edge, the data input sets the state to 1. The flip-flop ignores the data input at all times except during the clock edge. If the data input ever changes close to the clock edge, the flip-flop will store the value of the input from just before the clock edge. When we have a negative edge-triggered flip-flop, we add a complement circle to the diagram, and the state of the flip-flop will update only when the clock falls from 1 to 0. Let's recap. We created a sequential circuit called a D-latch or D flip-flop. The D-latch or flip-flop stores the value of the data input only when the clocking scheme permits the component to read the data input. Different clocking schemes will store the data differently, so we need to carefully choose our clocking scheme and how we send data to these synchronized sequential circuits.